All right, section 8.2. Again, this is a same thing that we talked about for the last section. It's a review section, really geared towards getting you ready for your next math class, Math 96. So this is all about reviewing function notation and graphing some nonlinear functions that we've graphed previously. So we have three objectives in this section. The first is to review function notation. The second thing is to find square roots. And the third thing is graph nonlinear functions. Now, I've put a star next to find square roots because we're not actually going to do that in this video, because we did square roots a long time ago, and then we did more square roots when we did our quadratics. So I'm not going to go over how to find square roots again. If you are unsure, you can go back and look at the old video for the old section, go back through those lecture notes, or come see me in office hours. But it's not anything new, just like all of these two sections have been. So I'm not going to do specifically that one. Now, function notation and nonlinear functions we are going to talk about because they're a little bit easier to forget, let's say. So in this first example, it says, using the graphs below, find the indicated value or values. So this is all about reading a graph and interpreting a function based on its graph. So when it says find f of 4, you can see this first one we're going to go into a little bit more detail. We come over to where x equals 4, and we look at the y value associated, because remember, the f of x notation, the function notation itself, was replacing y. And so when we look at this, when x is 4, y is 2. That's the point that's there. So this would be 2 as our answer. Same thing with negative 2. We come over negative 2, place our little point. When x is negative 2, f of negative 2 is positive 1. In C, g of 5, we come over to 5 and come up all the way to here. This is equal to 3. And g of 0 is equal to 0. So that's the base level identifying function values from a graph. Be able to go find the ordered pair and understand that the function notation, the g of something or f of something, is the y value. The x is the inside, and so you are always identifying the y value. Now in parts E and F here, we're finding x values. So it says find all x values such that f of x equals 1. The way that I like to do this is find the y equals 1, because that's what this is, and just put a little dashed line across. And you just go and plot everywhere where that crosses the function. And so we already knew one of them at x equals negative 2. And by doing this, we can also see that x equals 2 is going to work for that as well. And that would be our answer for part E. For part F, find all x values such that g of x equals 0. That's y equals 0. I'm just going to put a dashed line there. And then I just go identify all the points where that crosses my function. So we already knew that 0 was one of them. But we also now know that 3 is one of them, and negative 4. And again, this is just using a graph to interpret functions and remind ourselves that f of 4 is the y value, where 4 is the x value. Okay, moving on here. Use the graph below. Using the graph below, answer the following questions. So this is enrollment in degree-granting post-secondary institutions, in other words, colleges, 2-year versus 4-year. Our x-axis is fall semesters given by years, 2005, 2006, all the way up to 2014. Our y-axis is the number of students in millions, and this starts at 6 and goes up by 2s up until 18. So part A says approximate the 2-year enrollment in 2013. So we're looking at our 2-year graph here, and we come all the way to 2013 right here. And so what we're looking at is we are about right here on the y-axis. So we know that directly in the middle would be 7, but we're not directly in the middle. We're a little bit below half. So that means that we're slightly less than that. So I would say if we're slightly less than 7, considering we only have one number to go between then 7 and 6, I would approximate this to be about 6.5 million. Now, if you want to be a little different, you want to say, oh, I think that's more like 6.75. That's okay. Remember, this is an approximation, and there's a certain tolerance range where we would accept these answers, 6.5, 6.75. What we wouldn't accept is if you said 7.5 or if you said 7.9 or something like that, because it's clearly not that close to 8. Right? It'd be way up here if it was. And then in part B, we are asked, in fall 2007, the enrollment in four-year colleges was 17.1 million students. Find the increase in four-year college enrollment from fall of 07 to fall of 2011. So the reason they give us fall of 2007 is because if we look at the four-year fall 2007, this would have to be an approximation. So if they ask us this without this answer or this value of 2007 was 17.1 million, that means that we have to approximate this, which means that every one of us could get a different result, a different answer, because we were approximating. So by telling us it's 17.1, that's not going to change, because when we look at 2011, this is clearly sitting right on the 18 value for y. It's right there at the top. So that means we're doing 18 minus 17.1 to get a nice 0.9 million students. And that would be our answer for part B. So if we turn the page here, we are doing some graphing. These are all non-linear functions. So we have looked at or talked about all of these functions at one point or another. So I'm going to give myself some axes. And I'm going to be clever about this and do axes for all three right now. So I'm looking at each of these functions. Because they're nonlinear, we're going to adjust our axes. Notice that this is absolute value, so I don't need to even worry about negative y values, because there won't be any. So I'm going to scale by, I think just ones would be just fine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5. 2, 4, 6. Negative 2, negative 4, negative 6, 2, and 4. So we can do this a number of ways. We could just by plotting points. If I plug in 0, it's 0, 2. Easy to do. Plug in 1, that's going to be 0, or that's going to be 1, 3. Plug in negative 1. Negative 1 plus 2 is positive 1. Absolute value is still positive 1. Plug in negative 2, we get that 0. And then because this is absolute value, and everything stays positive, remember when we did absolute values back in a previous section, we said that this also mirrors itself. So when I go one further away from this 0, I'm going to match the y value of this point. And in fact, if you plug in negative 3, plus 2 is positive 1. Negative 4 is going to mirror this value here. Negative 4 plus 2 is positive 2. Negative 5 plus 2 is positive 3, and it mirrors this value here. And then we have our nice absolute value graph, which is just a V shape. This is why I have straight edges, so that my lines look better than that. And remember, my patented trick is just make your dots a lot bigger on your points if you don't hit through them in the line. And then label, so there's no question about what these points are. And we label the graph as f of x using its function name. And so we've graphed that. We can also use transformations like we talked about in the previous section, but plotting points here is just as good. So on the cubic, I have to worry about negatives and positives, so I'm going to give myself an x-axis right in the middle here. One, two, three, four, five, six. 2, 3, 4, 2, 3, 4, 6. So I'm actually going to scale these. Whoops, let's not forget this side. 6. I'm going to scale these by 2, so this is going to be 2, 4, 6, 8, 10. Negative 2, negative 4, negative 6, negative 8, negative 10. Negative 2, negative 4, negative 6, negative 8, negative 10. 2, 4, 6, 8, 10. So we're going to scale in this way specifically because when we're cubing things, it's going to get really big. And I want to make sure that I have enough space on my axes that I don't miss anything. So starting with 0, 0, 0, 0 cubed is 0. And then using 1, 1, 1 would be about here. Negative 1 cubed is negative 1. It would be about here. Then 2 cubed would be 8. Negative 2 cubed would be negative 8. Now we could continue on doing 327 and negative 3, negative 27. Obviously that's very, very large. These 5 points are typically what we graph when we graph a cubic. And again, use my patented make your points bigger, and then label 2, 8, 1, 1, 0, 0, negative 1, negative 1, and negative 2, negative 8. And this is labeled f of x. These 5 points, the negative 2, negative 1, 1, 0, and 2, they are the traditional ones. They're not the only ones you can do, but they are the traditional ones. Now we come to our last graph, square root of x. This is the square root. We have spent a long time talking about solving quadratics, i.e. using the quadratic formula with that square root, so we know there's not going to be any negatives here. So I can just look at the first quadrant. And I'm going to scale just by ones. 5, 1, 2, 3, 4, 7, 8, 9. And now we're just doing square roots. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. Why do I jump to 4? Because 2 and 3 are not perfect squares. And the next perfect square is 9, which is 3, way out here. And then we make this nice horizontal parabola. And again, we label our points 9, 3, 4, 2, 1, 1, 0, 0, and label our graph using its function name. So there's going to be some homework problems where you're graphing several different versions of these types of functions. Quadratics, cubics, or not quadratics, well, quadratics, yes. Quadratics, cubics, square roots, absolute values, stuff that we've been working with all semester. Again, this whole 2-section chapter that we do in chapter 8 is just a review, sort of, and a setup to kind of remind you of the things that are going to be extremely necessary when you start Math 96, so that you're not going in completely blind, because it's not something that you were thinking about, because we ended with, you know, solving quadratics or whatever. Okay, so that's the end of 8.2. Next up, we'll be starting our final chapter, chapter 15.